A particle is projected with a velocity 4I plus 12j meters per second from the origin. We want to find the position vector of the particle after 1.5 seconds. Let's draw a diagram of the situation. We'll draw some axes, and the particle is projected from the origin. The horizontal component of velocity is 4, and the vertical component of velocity is 12. The particle will follow a path like this, and after 1.5 seconds it may be at this point. We want the position vector of this point. Let's consider the horizontal motion first. No acceleration, so just s, u and t. We know the velocity horizontally is 4 meters per second. The time is 1.5 seconds until it reaches our point, and we want s. S is equal to ut, which is going to be 4 times 1.5, which is 6 meters. Let's consider the vertical motion. We know that gravity acts vertically downwards, and the magnitude is 9.8. We're going to take the upward direction as positive. So if we collect the information using SUVAT, then we have that u is 12. The acceleration will be minus 9.8 meters per second squared, negative since it is downwards and we took positive to be upwards. The time is 1.5 seconds and we want s. We can use s equals ut plus a half at squared. This is going to be 12 times 1.5, and a half of minus 9.8 is minus 4.9 times 1.5 squared. This calculates to 6.975 meters. The coordinates of this point then are 6 and 6.975, so the position vector is 6.975 meters, or if we want it in ij form, r is going to be 6i plus 6.975j meters. We now want to find the distance of the particle from the origin after 3 seconds. So in the first instance we need to repeat the previous process, but with the time equal to 3 seconds. So if we consider the horizontal motion, collect the information with SUT, we know the speed is 4, and the time now is 3 seconds. So S is equal to ut, which is going to be 4 times 3, which is 12 meters. Now consider the vertical motion. Collect the information with SUVAT. We know the time is 3 seconds. The acceleration is minus 9.8 meters per second squared, taking upwards as positive. U is 12 meters per second. and we want s. We can use s is equal to ut plus a half at squared. So this is going to be 12 times 3. A half of minus 9.8 is minus 4.9 times 3 squared. And this gives us minus 8.1 meters. So the particle is in a position like this. We want this distance. We can form a right-angled triangle, and we know this distance is 12 and this one 8.1. If we call the distance d, we can use Pythagoras' theorem. So d squared is 12 squared plus 8.1 squared. And this gives us 209.61. d then is the square root of 209.61, and this calculates to give us 14.5 meters, correct to 3 significant figures. Now in part C, we want to find the speed and direction of the particle when it is level with the point of projection. In other words, the particle goes up and comes down, and we want the speed and direction at this point. We know horizontally the speed is still 4. There is no acceleration horizontally. If there's no air resistance, it's also clear that the vertical component must be 12, because we're back at the same level. It will be 12 meters per second, but this time downwards. So if we look at this, the direction is 4 across and 12 down. The hypotenuse of this right-angled triangle will give me the speed of the particle, and the direction will be given by the angle theta. V squared is equal to 4 squared plus 12 squared, which is 16 plus 144, which is equal to 160. So V is the square root of 160, which is 12.6 meters per second, correct to 3 significant figures. Consider now theta. This is the opposite, and this is the adjacent, so we're going to use the tangent. The tangent of the angle theta is equal to 12 divided by 4, which is 3. Therefore theta is the inverse tangent of 3, and this is equal to 71.6 degrees, correct to 3 significant figures. So the direction of the particle is 71.6 degrees below the positive x-axis, as shown in our diagram above.